From a distance, 3I Atlas appears to be a comet, a glowing traveler tracing the edge of our solar system. But as scientists look closer, its metallic shine, strange tail, and chemical fingerprints suggest something far more complex. Is it ice, metal, or a relic from another star entirely?
Was this trajectory designed by some intelligence? Is it a spacecraft or a rock? We can tell the difference if we had enough data.
Today, we explore the mystery behind 3I Atlas. Interstellar Flash. October 2025. On the cold red plains of Mars, something strange streaked across the night sky. A flash so fast it outran the stars. At 0:03 a.m., UTC, NASA's Perseverance rover, recorded a burst of light moving at 37 miles per second. The event lasted barely a heartbeat, but it matched almost perfectly the predicted timing of an interstellar visitor, the Comet 3I Atlas. Within hours, every scheduled Mars orbiter, HiRISE, Mars Express, and the Trace Gas orbiter went silent. Their downlinks froze. The raw images vanished from NASA's public servers. The data blackout was instant and complete. But one man had already seen the evidence. Stephen Burns, a respected amateur astronomer known for his precision image calibrations, had been quietly downloading Perseverance's raw sky frames as they appeared on NASA's open access feed. He noticed something. A faint razor-thin streak cutting diagonally across the stars over Jezero Crater. Burns did what professionals often don't have time for. He checked everything. He matched the star field against the Gaia catalog, measured the separation between fixed stars, and confirmed the timestamps from Perseverance's right navigation camera, NavCam. The streak held consistent speed and direction across multiple consecutive frames. No pixel glitch, cosmic ray. For comparison, the fastest human-made object, NASA's Parker Solar Probe, only reaches 120 miles per second when diving near the Sun's gravity well. Here, at Mars's distance, an object moving 37 miles per second is off the charts. Too fast for meteors, constant for satellites, and too straight for artifacts. Burns carefully stitched the frames into a 9-minute time-lapse, overlaying them with Mars's star map. The streak didn't flicker or change thickness. It traced a clean, unwavering line. But one thing united them: Burns's track record. He wasn't a conspiracy chaser. Planetary researchers had cited his previous analyses on Mars dust storms and Phobos transits. That made his cautious tone matter even more. "Don't jump to conclusions," he warned. "If it's real, it'll stand up to replication." Still, his calculations didn't lie. The streak's timing, position, and velocity matched 3I Atlas's predicted sky path to within a few arc seconds. Even NASA's own tracking simulations put the interstellar comet roughly in that sector of the Martian sky on October 3, 2025, during its closest approach, about 18.6 million miles from Mars. And then came the silence. NASA's feeds stopped updating. ESA servers issued only under-calibration notices. No official statement came. Just a handful of quiet lines on public telemetry logs, and Stephen Burns's faint streak of light, cutting across the sky like a cosmic exclamation mark. Something had outrun the stars, and the story was just beginning. The viral verification wars. By dawn on October 4, 2025, the Mars sky streak had become the biggest unsolved riddle in modern astronomy. The question: did Perseverance really see 3I Atlas, or had everyone been fooled by noise? In the hours after Burns uploaded his 9-minute time-lapse, astrophotographers across the globe downloaded the same raw Perseverance frames from NASA's open access server. Some ran Python scripts to restack the images pixel by pixel. Others used commercial astrophotography tools like PixInsight and AstroImage-J. By midnight, dozens of videos circulated online, each claiming to reveal something slightly different. In others, the streak vanishes entirely. replaced by grainy noise patterns or speckled red pixels. The digital divide widened. Believers insisted the signal was consistent. Skeptics accused the others of overfitting, forcing noise to match expectation. Then came the flash. At 12:03 a.m., UTC, one analyst group from Poland, uploaded a stacked composite showing a brief green burst near the midpoint of the streak. It lasted for a single frame, roughly 3 seconds of recorded time, and then disappeared. The group claimed it was a real emission event, possibly from ionized carbon molecules flaring as 3I Atlas passed through sunlight. But the claim didn't survive unchallenged. American astrophysicist Ruth Delgado, known for her work on cosmic ray calibration for the Mars Reconnaissance Orbiter, immediately pointed out that the NavCam sensors aboard Perseverance were not color-true cameras. Their images were monochrome composites mapped through digital color profiles. That meant the green wasn't necessarily real light. It could be a processing artifact, an error caused by mismatched filter alignment during stacking. To test this, independent coders began to decompose the raw JPEG color channels and compare intensity histograms. They found inconsistencies, small variations in bit depth that could easily simulate a colored flare. Still, some insisted the flash had physical plausibility. Comet emissions often produce green glows from diatomic carbon, though none had ever been detected this sharply or briefly from Mars. He joined a live stream that night, repeating his mantra, "Replication before revelation." He urged everyone to share code, publish workflows, and cross-check timestamps. He even posted his plate scaling spreadsheets for others to audit. His openness kept the peace for a while. But within 48 hours, the conversation spun out of control. One viral X thread accused NASA of pulling raw data to hide alien evidence. Another claimed ESA had confirmed multiple fast-moving tracks in its own Mars Express imagery. A rumor quickly denied but impossible to fact-check while official data channels remained frozen during the U.S. government shutdown. Some claimed to find secondary streaks, parallel traces suggesting more than one object. Others reported nothing beyond noise. Statistical models flew back and forth. Some estimated a signal-to-noise ratio near 5:1, barely above threshold for confirmation. Others measured it below 2:1, indistinguishable from background dust. Even the most rigorous analysts agreed. The evidence was suggestive, not conclusive. Mars's silent window. By the time the online debates reached a fever pitch, Mars itself had gone silent. For nearly a week after the October 3, 2025 flyby, no new orbital data appeared. The Perseverance NavCam feeds stopped updating. The HiRISE, Cassis, and Mars Express portals went quiet. Even routine calibration images, the kind that normally trickled in daily, froze in place. Behind the scenes, engineers at NASA's Jet Propulsion Laboratory and ESA's Mission Control in Darmstadt were locked in a tense balancing act between science and caution. The flyby of 3I Atlas had been a first, an interstellar object passing within 18.6 million miles of another planet. 3 orbiters had been retargeted to capture it, each one pushing beyond its normal design limits. The HiRISE camera aboard the Mars Reconnaissance Orbiter wasn't meant to chase moving targets. It was designed for static terrain, cliffs, dunes, and rover routes. To catch an object moving 37 miles per second, the team had to rewrite its imaging sequence scripts. Each exposure became a gamble of geometry. Aim too early, and the object would be out of frame. Too late, and it would already be gone. Meanwhile, ESA's Trace Gas Orbiter and Mars Express were tasked with a parallel mission, spectral analysis. They weren't taking pictures, they were listening to light. The goal? to measure the chemical makeup of 3I Atlas's coma and jets during the flyby, but that required knowing exactly where the comet was at every second. The workload was immense. Every orbit, engineers had to slew their spacecraft off normal alignment, turning away from Mars to aim at a speck of moving light. These maneuvers were energy expensive, risky, and had to be commanded hours in advance with no real-time feedback. The orbiters couldn't track automatically. They could only look where Earth told them to. And then, right as the flyby approached, came a 1-2 punch. A solar particle storm on October 2nd disrupted downlink timing from the Mars Reconnaissance Orbiter. The next day, the U.S. government shut down suspended non-essential NASA communications staff. The result, a perfect communications chokehold. They also knew that releasing uncalibrated frames, full of cosmic ray hits, hot pixels, and smears, could ignite a scientific disaster. So they slowed down. Inside Building 264 at JPL, a small calibration team worked frame by frame. Each high-rise image was checked for registration drift, geometric distortion, and radiometric noise. Every frame that showed a streak, spot, or flare had to be manually verified against predicted orbital motion. Even a single cosmic ray strike could mimic a companion object. As one imaging lead later put it in an off-the-record quote, "Outside these labs, the silence was deafening. Forums fumed. Amateur scientists demanded transparency. Some called it bureaucracy. Others whispered of censorship. But inside the control rooms, the truth was more technical than conspiratorial. For the first time, mission teams were calibrating images of a hypervelocity interstellar object using pipelines designed for stationary terrain. Every line of code had to be rechecked. Every correction map is recalculated. Cosmic rays, dust scatter, and even Martian twilight reflections had to be isolated from the real signal. The silence wasn't secrecy, it was self-preservation. Every image, every spectrum, every telemetry packet was a potential headline. And until the teams could be sure what the data actually showed, no one wanted to be the one to say, "We caught something that shouldn't exist." The chemical contradictions. When the first spectral packets from Mars orbiters finally trickled down to Earth in mid-October 2025, scientists expected to see something familiar, the chemical fingerprints of a comet. Instead, what they found didn't match any known comet in the solar system. After weeks of calibration, the Mars Express Planetary Fourier Spectrometer and the Trace Gas Orbiter's NOMAD instrument began to transmit partial datasets from the 3I Atlas campaign. The signals were faint but distinct. When converted into spectra, they painted a picture that baffled comet scientists. Normally, comets that approach the sun begin to shed their icy outer layers, releasing water vapor, carbon monoxide, and carbon dioxide in predictable proportions. The dominant emission lines come from H2O and C2, the latter responsible for the bright green glow seen in classic comets. But 3I Atlas broke that rule entirely. The Mars Express team noticed something shocking. The C2 swan bands were missing. Those are the spectral lines at 516 and 563 nanometers that almost every comet exhibits when sunlight breaks down dicarbon molecules. Instead, the emissions around that wavelength were faint or absent. Yet several Perseverance frame stacks, and even some high-altitude orbiter frames, hinted at a greenish hue around the object. A green glow without dicarbon shouldn't exist. When the team compared notes, they found the main emission peaks clustered around nickel and carbon dioxide, with almost no H2O vapor. That was a massive deviation from the cometary template. Typical solar system comets have iron stronger than nickel by at least a factor of 10. In 3I Atlas, nickel dominated, inverting that ratio, and water, usually the most abundant component in an active comet, was nearly absent. Dr. Elena Varga, a planetary chemist at ESA, called the result a chemical riddle with no right answer. If nickel were that abundant, it implied a formation zone far richer in heavy metals than our solar nebula, a world forged around a metal-heavy star, perhaps one that went supernova billions of years ago. The implications were staggering. If 3I Atlas came from such an environment, it might be a fragment of a planetary crust, or even a remnant of a destroyed exoplanet core. That could explain its unusually high density and stability despite visible jetting. But there was another layer of mystery. In other words, the outgassing, the thrust that normally nudges comets slightly off their predicted paths, was either incredibly weak or perfectly balanced. That meant the jets seen by Mars orbiters weren't affecting its trajectory at all. Theories multiplied. One camp suggested electrostatic emissions, high-voltage discharges between surface regions of different potential, producing short-lived green flares without traditional chemistry. Another proposed metal vapor luminescence from nickel compounds ionized by solar radiation. Both would be new to comet science, and both could explain why the flash seen in the Perseverance images looked more like an electrical arc than a gas plume. Meanwhile, Trace Gas Orbiter's infrared spectrometer detected unusually strong CO2 outgassing 10 times higher than any recorded water vapor line. That made 3I Atlas the first known object where carbon dioxide drove activity instead of ice sublimation. The chemistry looked more like something from Venus's atmosphere than a comet tail. Inside ESA, debates turned fierce. Was 3I Atlas a comet at all, or an interstellar asteroid masquerading as one? If its metallic core was venting gases through microfractures instead of evaporating ice, then its entire classification was wrong. NASA's Spherex telescope data, still being processed, hinted at similar anomalies. Low reflectivity in near-infrared and unusually high polarization. Possible signs of dense metallic particulates. The working hypothesis: a nickel-heavy, carbon-rich body with traces of cyanide and silicate dust. A chemical cocktail unlike anything born in our solar neighborhood. The shape of controversy. By early October 2025, one image from Mars dominated every discussion about the interstellar visitor 3I Atlas. A faint streak captured by NASA's Perseverance rover had become the subject of argument across the scientific community and public space alike. What the picture actually showed, and what it didn't, soon became a test of how science handles uncertainty under the glare of worldwide attention. The frame in question was taken by Perseverance's right navigation camera, NavCam, on October 4th, 2025, at roughly 21:33 local solar time. It appeared in the rover's publicly accessible image archive as a single line of light cutting across the Martian starscape. That alone would not have drawn notice, except that the date coincided exactly with 3I Atlas's closest pass to Mars, about 18.6 million miles away. The match in timing was too close to ignore. Many concluded the rover had just recorded an interstellar comet streaking across the Martian night sky. However, the image was never confirmed by NASA or JPL as depicting 3I Atlas. The agency remained silent, its communication offices restricted by the government shutdown that had furloughed much of its staff. In that information vacuum, speculation grew faster than data. Some observers pointed out the streak's remarkably straight shape and uniform brightness, unusual for a meteor or cosmic ray artifact. Others argued it was too geometrically perfect to be natural. When Harvard astrophysicist Avi Loeb reviewed the frame, he provided the first detailed technical explanation. Writing on his research page, Loeb described how the cylindrical appearance could easily result from long integration times and image stacking. Perseverance's NavCam, he explained, takes rapid sequences of short exposure frames, which are later combined digitally. During that process, any bright moving object crossing the sky would appear stretched into a single linear feature, a motion smear. Loeb calculated that, at the comet's distance and velocity of roughly 130,000 miles per hour, the resulting streak would appear tens of thousands of miles long in projection. That made it an artifact of movement, not an object of that shape. Independent analysts confirmed the same principle. Each individual navcam exposure was less than 4 seconds, but when hundreds of those frames were stacked over several minutes, the combined light trace lengthened dramatically in a single snapshot. 3i Atlas would have looked like a tiny dot. Only the stacking process made it appear elongated. JPL imaging specialists backed that interpretation when questioned later. They emphasized that the navcams were never designed for astrophotography. Their main purpose is navigation and terrain mapping, not distant object tracking. Even at the comet's closest approach, its apparent size from Mars was so small that no surface structure could have been visible. The streak, they said, represented light integrated over time, not a resolved image of a physical body. Still, the public fascination was impossible to contain. Discussions in astronomy forums focused on the difference between real imagery and stacked composites, a distinction often lost outside professional circles. Within the research community, most agreed that the Perseverance frame had captured the light from 3i Atlas, but not the comet itself, only its apparent path across the sky during a long imaging sequence. As more technical explanations emerged, the narrative slowly returned to ground. The cylinder lost its mystique. The data regained its context. But the episode exposed something deeper: how quickly a scientific image can transform into a story the moment the facts fall behind public curiosity. What Perseverance actually saw was simple: a moving light crossing a stationary sky. What the world thought it saw was far more complicated. Beyond comet models. When the orbital and photometric results from ESA's Mars Express, TGO, and NASA's SphereX mission were finally compiled, the portrait of 3i Atlas that emerged didn't look like any comet ever recorded. Its path, mass, and jet geometry defied every predictive model scientists trusted. The first anomaly came from trajectory tracking. Using precise astrometric measurements from the Mars Reconnaissance Orbiter, researchers plotted the object's position over 10 consecutive days. Normally, an active comet shows small deviations from pure gravity, tiny thrusts caused by jets of gas and dust venting into space. But 3i Atlas didn't budge. Its trajectory clung to a perfect gravitational arc, as if no outgassing was happening at all. That meant one of two things: either its activity was purely visual, or its mass was so enormous that jet thrusts couldn't move it. When orbital analysts ran the numbers, the results stunned them. Based on the absence of detectable acceleration, they calculated a minimum mass of 10 billion tons, the equivalent of a mountain drifting through interstellar space. But even more baffling was its behavior under sunlight. Standard comet physics predicts that tails and jets always stream away from the sun, as radiation pressure pushes dust and gas outward. Instead, images from Mars orbiters showed a narrow, forward-pointing plume aimed toward the sun, a configuration called an anti-tail, but far sharper and denser than any on record. The plume appeared to lead the comet's direction of motion, with a sharp brightness gradient that faded over only a few hundred miles. Dynamic simulations failed to explain it. For the jet to maintain that shape without dispersing, the source would need to be exceptionally dense and cohesive, more like solid rock than a loose cluster of ice and dust. If 3i Atlas were truly venting gas at that velocity without spinning apart, its structure had to be metallic or composite, not porous. In other words, it behaved more like an asteroid wearing a comet's coat. Then came the light curve analysis. Over a month of observations, the object's brightness remained nearly constant, even as it passed closer to the sun. comets brighten dramatically as their volatile ices vaporize, but 3I Atlas barely flickered. Its reflectivity stayed stable, suggesting either a low albedo surface covered in carbon-rich material or a coherent metallic crust that resisted sublimation. Astronomers began calling it the stubborn comet. Others dropped comet entirely, labeling it an interstellar planetoid, a rogue planetary fragment that had been ejected from another solar system. Its velocity, about 130,000 miles per hour relative to the Sun, ensured it would never return. Once it passed perihelion on October 29th, it would slingshot back toward interstellar space, lost forever. But one correlation turned skepticism into wonder. Dr. Avi Loeb's research team at Harvard ran orbital simulations tracing 3I Atlas backward through time using Monte Carlo models. Their results showed a 0.6% probability that the object's path intersected the same sky coordinates as the 1977 WOW radio signal, the 72-second narrowband burst detected near the 1,420 MHz hydrogen line. It wasn't proof of anything, but it was enough to raise eyebrows. If an interstellar object had crossed that region decades after a signal from the same coordinates, coincidence or not, it deserved attention. Loeb's group urged radio monitoring during 3I Atlas's approach to perihelion. SETI researchers coordinated to scan the hydrogen line frequency, the channel most often associated with artificial signals. Nature rarely emits narrowband radio at that precision. If anything reappeared, it would be a sign, not of aliens necessarily, but of non-random structure in the noise. Nothing came through, only static. But the alignment, the mass, the jet direction, and the silence, all of it painted a picture of an object that didn't fit inside any existing box. As one planetary scientist put it in an ESA debrief, "If it's natural, it's the strangest natural object we've ever seen. And if it's not, we need a new word for what it is." Into the solar shadow. By October 29, 2025, the sky went quiet. The interstellar object 3I Atlas had slipped behind the Sun, a vanishing act written into celestial mechanics. For 5 weeks, until early December, no telescope on Earth or Mars could see it. The red planet's orbit had rotated it directly into the Sun's glare, making observation impossible. The silence was not mysterious this time. It was astronomical inevitability. But that didn't make the waiting easier. In mission control rooms from Pasadena to Darmstadt, teams watched their screens fill with empty coordinates. They had tracked the object's path, measured its light, dissected its spectrum, and argued over what it was. And now, there was nothing left to see. The last confirmed detection came from the Trace Gas Orbiter on October 28th. A faint spectral reading, barely distinguishable from background noise, confirmed the comet's trajectory as it passed its closest approach to the Sun, about 130 million miles out. After that, its signal was drowned in solar interference. The disappearance was routine, but the anticipation wasn't. Every team, NASA, ESA, and dozens of independent observatories, was preparing for the reappearance window in December. That short span before dawn, when 3I Atlas would emerge from the solar halo, would decide whether the past month's chaos ended in clarity or deeper confusion. For scientists, the objectives were clear. 4 critical measurements would make or break the theories. Brightness, had the object dimmed, meaning fragmentation. Trajectory, did it still follow the same gravitational curve, or had hidden jets altered its path? Morphology, did it retain a single nucleus, or had it split apart? Spectral fingerprint, did its chemistry evolve as it approached the Sun? Each data point would either confirm a natural origin or keep the mystery alive. Meanwhile, SETI researchers at the Allen Telescope Array and Green Bank Observatory kept their antennas locked on the predicted coordinates. They weren't chasing alien contact per se. They were chasing coincidence. The WOW signal correlation from Loeb's team had ignited a cautious hope. If any narrowband transmission appeared during re-emergence, even briefly, it could hint at something extraordinary. None did. All that came through were solar radio bursts and background hiss, but in the absence of a signal, meaning can be deceptive. Some argued the silence was proof of normalcy, a comet doing what comets do. Others said it was the quiet before revelation, a pause in a longer story. For the public, attention had already drifted. New headlines had replaced 3i Atlas, politics, storms, celebrity scandals. The once blazing cylinder over Mars memes had faded into digital archives. Yet in the scientific world, the data was still being poured over, frame by frame, photon by photon. The strange chemistry, the anti-tail, the nickel-heavy emissions, all climbed partway up, but none reached the top. There was motion, there was mass, there was mystery, but nothing yet that crossed into the realm of deliberate design. By the time December rolled around, anticipation turned to patience. The comet would emerge again in the morning sky, fainter but still traceable, before fading forever into deep space. When that happened, astronomers across the world planned a synchronized observation run, a final farewell sweep using radio, optical, and infrared telescopes. The irony wasn't lost on anyone. Mars, once the observer, would now be blind. Earth, once the bystander, would take up the watch. And maybe, if the data aligned, the full picture of what Perseverance saw that night, that thin streak outrunning the stars, would finally make sense. Until then, the scientific world lived in suspense, the kind born not of conspiracy but of cosmic humility. An interstellar object had crossed our neighborhood, whispered secrets in strange spectra, and vanished without a trace. As one mission lead wrote in a private note later shared with Science Weekly, "The hardest part isn't the silence. It's knowing we may have caught a glimpse of something historic, and now we'll never see it again." 3i Atlas was gone, racing beyond the reach of human eyes. Whether comet, fragment, or something we don't yet have a word for, it left behind a single truth. Even in an age of data and precision, the universe still knows how to keep a secret. Thanks for watching. If you enjoyed this deep space mystery, hit like, subscribe, and ring the bell for more cosmic updates on 3i Atlas and other interstellar discoveries.